I'm very glad also that I could make it physically. So I'm looking forward for interaction, human interaction. It's a pleasure to start this conference. And of course, this is a conference on Poisson geometry. The first slide should be the definition of a Poisson manifold. I will need to write it down because I will build on it. We will go to the infinite dimensional case in a few moments. So let me just write it here because I will use it afterwards. So a Poisson manifold, as you know, Poisson manifold M is, in my case, it will be a Banach manifold, a Fréchet manifold, or a manifold a manifold constructed using chart from locally convex spaces, but anyway, is a manifold M endowed with bilinear mapping. So rare to write on blackboards. I'm not used to it anymore. So the bracket, we take functions, smooth function of the manifold. Give a function for skew symmetry. And the Leibniz rule. So what are the problems if you start with this definition in the infinite dimensional case? So of course, I have noted here equation of function. When you start with a Hamiltonian, you get dynamic on your manifold. This is where we want to go, but on an infinite dimensional manifold. So the first thing is there's a golden rule in infinite dimensional geometry. Each time I give a talk on this topic. So the golden rule is never believe anything that you have that proof. So there are mistakes in the lecture, so you have to go into the proof to check every details. Some pathologies of infinite dimensional geometries are, for instance, that the distance function that you get using a Riemannian metric on manifold may be degenerate zero function. So you may define a well-defined Riemannian metric on an infinite dimensional manifold, but anyway, what the distance function that you get is zero. So this was first showed by Michaud and Munford in shape analysis. Other problems in Riemannian geometry, there may not be a Levi-Civitella connection. Hopf-Frino theorem does not hold in general. And for us, more problematic, there is no local equivalence of symplectic forms. In the infinite dimensional setting, there are some strong symplectic forms, some weak ones, and they are not equivalent. There are no Darboux coordinates in this setting. Problems in complex analysis, there are formally integrable complex structures that do come from holomorphic charts. We will discuss it in a moment. The tangent space differs usually from the space of derivation, even on a Hilbert. what I will show you is a Poisson bracket that is not given by a bivector field. Also, that cannot be enlarged. So let me go through the problem also coming when you on a non-separable Banach space. Usually on a non-separable Banach space, and we will see example like L infinity of H, when H is a bounded operator on a Hilbert space. It is an example. So there are no bump function available. And they're meaning in particular that you cannot localize things because you don't have these band functions. There are also derivations of order greater than 1. I will give you an example. And as I said, there are Poisson brackets that are not given by vector fields. And also, Hamiltonian vector fields are not automatic. I mean, the existence is not automatic. So a queer Poisson bracket, so this terminology is coming from the book of Kriegel and Micho. It's a Poisson bracket not given by a bivector field. So let me give you an example. We start with the space, and the kinetic tangent space is made of vectors are equivalent classes of curves. So you draw a curve on your Hilbert space here, and you on this space of curve when they have the same derivative at 0. This is a kinematic tangent space of equivalence classes of curves. This goes through also to the Banach manifolds. There are also operational tangent vectors. So these are derivations. These are linear maps from the germ of smooth function. Here, C infinity of H are germ of smooth function defined around X. So D is a linear map from this space of germs of smooth function into R, satisfying the Leibniz rule. And so I need to use some very common theorem of functional analysis to prove this existence of. It's coming from the book of Kriegel and Micho. So the ingredients are the following. So there is a consequence of Riesz theorem. The Riesz, as you know, is here, telling you that the dual space of a Hilbert space itself. So in particular, if you take a smooth function f and you look at this second derivative of f at a point x, x is in your Hilbert space. This is a bilinear form. And it can be written using the scalar product of the Hilbert space, like this, using the scalar product and a bounded operator A. And since, so that's the first consequence, so there exists an operator A for A, a bounded operator on H. So that's the first thing. The second ingredient that we need is a consequence of the fact it's probably written before. The Hilbert space is supposed to be infinite dimensional. So the consequence of the infinite dimensional assumption is the fact that the set of compact operators K of H included but differs from the space of all bounded operators. These are bounded. In particular, if you take the identity, which is not compact, because we are on the infinite dimensional Hilbert space, it's not inside K of H, so we can separate the identity and the subspace K of H. So perhaps you can follow it. Using then Hahn-Banach theorem, so this is a consequence of Hahn-Banach theorem. There is a functional L. Yes. There exists L smooth functional on B of H, such that its value of on the identity is 1, and its value on K of H is 0. So it separates the identity and K of H. Oh, sorry. Oh. Yes. So now we define the operator G. By the formula, we apply this functional L on the second derivative of f at the point x. You see that this operator takes the second derivative of f, so it's of order 2. And now if we do the computation of the Leibniz rule, so first we have to differentiate once to get the differential of the product of two functions. But when we apply a second derivation, as you see, you have the second derivative of f here, and the second derivative of g here, but you have also this first derivative acting on a vector of f, and the first derivative of g acting on a vector on g. So these middle terms actually are rank 1 operators, so they are compact. And if you apply L on these, it will give you 0 because of this condition that L on compact operator is 0. In particular, on finite rank operator, L is also 0. So L kills middle terms, and what remains is only the functional L applied to the second derivative of f, which is exactly the derivation that we had, d, and also L applied to the second derivative of g, which is dg. So Leibniz rule is satisfied, so this operator d is a derivation of order 2 in this Hilbert space. Using this, it's quite easy to define a Poisson bracket which is queer in the sense that it uses the function at order 2. So we just extend this Hilbert space with one dimension. So we're looking at h times r. So points in this manifold h times r are points in the Hilbert space plus real coefficient. And so the Poisson bracket that we have here is just a combination skew-symmetric combination of this square derivation, this operational derivation here, and the usual derivation with respect to the extra parameter lambda. Because when you look at this Poisson bracket and you compute the Hamiltonian vector field associated to the function given by minus lambda, so the extra dimension that we had, then you get exactly this square operational tangent vector. So this will act using the second derivative of functions. So there's no way that this Poisson bracket could come from a bivector field, which is by definition a field that a bivector field is taking the element of tangent cotangent space to M. So no way that there is a Poisson tensor behind this Poisson bracket. Is this clear? Do you have questions? You see, it's a very easy example on the Hilbert with this square operational tangent vectors. If there's no question, I will go back to the definition here. And yeah, please. Yeah.
All the Hamiltonian derivations comes from vector fields. Does the Poisson bracket comes from a bivector field?
Yes, this is very strong. Yes, yes. This is an assumption that people do, which is quite strong. Yes, but you can do this. Yeah, we will see this in the definitions of infinite dimension Poisson manifolds. Yeah, let me give a list of people that were working or are working on it. Poisson geometry, for instance, predual of work of Matthew, dual of locally convex Lie algebra and loop groups, that's in the work of Nib, Salman, and for people for doing PDEs, they have another approach, which is doing Poisson geometry or even simplified geometry on a vector space, but using functions that are defined on a dense domain. So in this work by De Bièvre, they have a domain on which everything is defined, but the functions are still smooth outside. Yes, so that's more from a PDE point of view. For me and my collaborators, Tomasz Goliński, we are interested in the interplay between functional analysis and Poisson geometry, and in particular Poisson geometry on group like U of H, or a restricted version of these, so groups of unitary operators or on space, group of this kind. But people from like Kessin Misiolek are also interested in Virasoro algebra, diffs of S1, or another group, Laurent, Jean-Wu, and Reznier, who are interested in infinity of M, where M is a finite dimensional symplectic manifold. And I'm sure I forgot a lot of people. Sorry? Perhaps infinite, finite? Yeah, I don't know. No, they want a Poisson structure on here. Yeah, use it. Yeah, another level. Yes, they're using the symplectic structure of M and put a Poisson structure of C infinity of M. So functions. Indeed. Okay. Sorry? So this one is symplectic. So depending on the definition of everybody. So now we'll go to the definition, because the point is there are possible extension to infinite dimension of the definition which is here. So let me give you the definition of Nib, Salman, and Timan that I took from the paper. So the first thing that they do, instead of looking at C infinity of M, they take A inside C infinity to F. This will be the space of admissible functions. So A is supposed to be a unital subalgebra, so meaning that it's stable by pointwise multiplication. What they call unital. So they take a space of admissible functions. You see a Poisson bracket. P1 is exactly the same as we had in the finite dimensional case. There is skew symmetry, Jacobi and Leibniz. Leibniz rule for this, you need that the A is stable by pointwise multiplication. Then there is a P3, which goes to exactly the compensate. P3, in this definition, the existence of a is required. There is another condition P2, which I will explain. But for this, I can erase here. And I will give a definition first. So A, let's say that A is a unital subalgebra of C infinity of M. M is an infinite dimensional manifold. The first set of A, I will denote it G1 of A, is the subbundle of T star M, whose fiber over a point, so the fiber over a point P in M is given by all the differential of function in A at this point, is a space of differential function in. So this is basically the space that you get when you look at differential, so at point P, you take a point P, the differential of function in A, and that's a subspace inside T star M. And what you need, this is P2, the condition P2, you need that A is large enough. Now I can erase this definition. And I will write the definition of duality pairing, which is really the central notion in infinite dimension. So let's say G plus and G minus, let's say Banach, Fréchet, whatever you want. vector spaces. A duality pairing between these two spaces is simply a non-degenerate bilinear mapping. And this will take the role of duality pairing. So non-degenerate means that if you start with x and y equal to 0 for every x in the first space, this implies that y is equal to 0. And reverse, if x and y is equal to 0 for every y in the second space, then this means that x is equal to 0. So a consequence of this definition is that G plus can be seen, I should have written continuous here, depending on the category that you're starting with, Banach, Fréchet, or whatsoever, you need non-degenerate continuous linear mapping. And with this condition, G plus is actually can be seen as a subspace in the dual of G minus. And also, G minus can be seen as a subspace in the dual of G plus. Okay, so now this space of first jet of the admissible functions need to be large enough to be to separate points in T of Tm. So let me give you a definition. Unital subalgebra A of C infinity of M is said to be large if and only if the pairing, the duality pairing between Tm and T star M restrict to duality pairing between Tm and the third jet of A. And now you can understand this second definition for every element of the manifold and every tangent vector satisfying that the differential of your admissible function applied to this vector is 0 for every function which is admissible, then V is 0. This is exactly the non-degeneracy of the duality pairing between Tm and the first jet of the admissible functions. So this is the condition required. So now, this is a definition of Nib-Salman-Timan, which is not appropriate for my case, because as I told you before, in my case, I'm working on non-separable Banach spaces where the bump function may not exist. So even working with C infinity of M is a nightmare, because I can just not, if I start with a function defined locally, I cannot extend it smoothly on the whole manifold. So I don't have bump function for that. So the definition that I propose is the symmetric definition, so very almost equivalent to the definition before, but seen as from the point of view of subbundles. And also I start with Poisson tensor because, as I show you, if you start with a bracket, there may not be a Poisson tensor associated to that. So for the purpose that I have, I need a Poisson tensor. So I define what it is. A Poisson tensor is a smooth section of the bundle of skew symmetric bilinear maps eating element of F. F is a subbundle of T star M, which is in duality with Tm. And so you have Jacobi identity. It's exactly the same, but you have to make sense of this differential of the Poisson tensor applied to closed local sections of F. But that's exactly the same Jacobi identity. And this has to be satisfied for closed local section of a subbundle F in T star M. So why is it closed here? So the condition closed is, if you think about it, Jacobian identity is on functions. So if you write the Jacobi identity on the Poisson tensor, it will be satisfied only on differential functions. So that's why here we use closed local section. This Jacobi identity doesn't hold for general section of F. And now we have the same definition as before for a Poisson manifold. So we ask for a Poisson tensor. So again, we have a subbundle of T star M. So you can think at, for example, the first set of the space of admissible functions on which a Poisson tensor is defined, and it is a smooth section. Yeah, please. So the only thing that I don't ask is P3. So in my case, I didn't put this assumption. And I still don't know if it's a good thing to put it or not.
No, but I'm just wondering if weakly selected with it, which is only weakly non-degenerate, do they fit into this definition?
Here, the existence of Poisson tensor is not assumed. So they may have problems with non-existence of Poisson tensor. That's one of the points.
That it would have functions or in the image of the two-point. Either Poisson brackets maybe would be defined, and this would be the subalgebra.
Exactly. So that's the link. Yes. So exactly. So this F in this definition is the first jet of A. This is a link. So as I said, it's just the dual perspective of bundles. And so we can go back and take in T star M. You can reconstruct admissible function will be those whose differential is. So you can go back. But as I say, I'm not working on C infinity of M. It's local. You can also adapt this definition and say you localize the bracket is localizable. So if you restrict yours, if your function defined on open sets that are included, the bracket is also included. Yeah, you can also work like this, but that was not my point of view. Other questions? Is this definition quite clear, or almost clear? Yes? It's not difficult, right? So with this definition, a symplectic manifold is naturally a Poisson manifold, of course. So we had this problem that for weak symplectic manifold, the range of this sharp map is not the cotangent space. So here you put F equal to this image of the sharp map, and the Poisson tensor is naturally finite. So Banach symplectic manifold are examples, and also you can work on Banach Poisson spaces. The original definition of Otsiewicz and Ratziu uses G and G star, but can be more general and use spaces that are just in duality, G plus and G minus. And so you have a Banach Lie algebra, G minus, which are continuously on G plus, which is in duality with G minus, by coadjoint action, and you ask that this coadjoint, this at star is also continuous. Okay, so let me go through finite dimensional Poisson Lie group, which is a subject that I wanted to connect to KdV equation. So you know, probably all of you, this equivalences of triple Lie algebra and connected, simply connected Poisson Lie group. So let me go through this, starting with an example, which are, so I will, which will, so it's easy to generalize. For example, group, so space of skew matrices. It's in duality with another algebra, which is Lie algebra formed by upper triangle matrix. And the duality pairing is given by the imaginary part of the trace, which is non-degenerate here on the space of all matrices. And the block UN and BN are both isotropic for this duality pairing. So this is the prototype of a Manin triple. A Manin triple is a triple of Banach Lie algebra. I put the definition already in the infinite dimensional Banach setting. So three Lie algebra. G is the sum of G plus and G minus. There is a non-degenerate symmetric bilinear mapping, which is invariant with respect to the brackets on G. And both G plus and G minus are subalgebra and isotropic for this bilinear map. No difficulty here. Okay, so that's definition in linear algebra, and you know that if you start with a Poisson Lie group, when you undo it with a Poisson structure which is compatible with group multiplication, you start with a Lie group, undo it with a Poisson structure, and you ask for compatibility with a group multiplication. So, for instance, SUN is an example of this. Then you can pull back the Poisson tensor to the identity using right translation. So you define a map which go from the group to skew symmetric maps on G by pulling back to the identity. And this map, if you differentiate it, you will get a cocycle on G. So this is a cocycle identity. So this is just coming from the differentiation, and this is the definition of bialgebra is coming from this. Bialgebra here is a Lie algebra whose dual space, a bracket, and such that we have this cocycle identity. That's the finite dimensional setting. What we have in the infinite dimensional case, it's a bit more tricky. So man in triple stays the same definition. Lie algebra stays the same definition, but let me go give you this example of finite dimensional man in triple. You have each other. Here it's turned out that C exactly as the product of UN and Bn. UN and Bn are the dual Poisson-Lie group of each other. Using Iwasawa decomposition, you have this system. So you have action of B on UN and on U on Bn. And this is what we want to have in the infinite dimensional setting. What we have is as I said, I want to connect to the KdV equation, but before that, perhaps I should I should give you the setting in the what we get. Let me go through this. I will come back to this after. Yes, this is the slide that I wanted to have. In the infinite dimensional setting, you start with a man in triple. What is equivalent to man in triple is two things. You have a Banach-Lie by algebra, the same definition as the finite dimensional case, but some condition which give the notion of Banach-Lie Poisson space. So these two ingredients, Banach-Lie by algebra and Banach-Lie Poisson space, are equivalent to the linear definition of man in triple. If you start with the Banach-Poisson-Lie group, so again, the same definition, Lie group with a Poisson tensor which is compatible with multiplication. If you just start with a Banach-Poisson-Lie group, you will get a tangent Lie by algebra. If you ask moreover that the Poisson tensor takes value in the tangent space of G, then you get a Banach-Lie Poisson space out of it, and this is equivalent to the man in triple. So there is the stability of the cotangent space that is included in the Banach-Lie Poisson space condition. So why I'm doing all of this? I'm interested in PDEs. And the one that I'm interested in mostly is the KdV equation, which is this equation of swallow water dynamics. You can write it as a lax pair using this decomposition. P here is third order operator, differential operator, and L is a second order differential operator. Here D is derivation with respect to the space variable. This P is in fact, if you take L, you take the square root of L and to the power 3, and then take the differential part of it, you get P. So let me go through this. The square root of a differential operator L is a pseudo-differential operator sequence of D plus some integral operator D minus 1 and so on, such that if you take the square of it, you get L. And the plus is you have a pseudo-differential operator, so positive powers of D and negative powers of D, and the plus kills all the negative powers of D. So as you see here, you have a lax pair with a power of L, and you have all the hierarchy of equation if you replace the 3 that was before with an integer. So what I wanted to do is to understand this equation using Poisson geometry on a U of H, represent version of U, where A is the separable space. And this will connect with some Grassmannians. So let me give you a definition of the restricted Grassmannian. Spaces of H is a separable Hilbert space that are not too far from a given one. So you take H plus your preferred Hilbert space. In this case, actually, the Hilbert space is explicitly L2 of S1 into C, a complex square integral function on the circle. And the decomposition H plus and H minus is the following. H plus are those functions that can be extended holomorphically inside the disk. H minus are functions that can be extended holomorphically inside the disk. And so restricted Grassmannian are those spaces that are not too far from H plus, meaning that the projection from your space to H plus is spread on almost invertible modulo Hilbert-Schmidt. Okay, so this Grassmannian is a homogeneous space in two different ways. Unitary group, restricted in the sense that the off blocks are Hilbert-Schmidt, and so homogeneous space of this unitary group, and also an homogeneous space of general Banach-Lie group, also with off blocks. Sorry for that. Hilbert-Schmidt. Particular, what we need is the action of the space of operators which are triangular with respect to the very natural basis of the Hilbert space H, with strictly positive coefficient on the diagonal. This space acts on this Banach-Lie group acts on the Grassmannian, and actually there is a subgroup inside here which is inside the disk satisfied f of 0 equal to 0, and if you take the exponential of this kind of function, you get element of a group which acts by operators on the space and also on the Grassmannian. And you see that this group is commutative, of course, and this T1, T2, T3 are different times that give you the different flows of the KdV hierarchy. So the connection is a bit tricky. It doesn't matter for here. What is important is that this group, this commutative group, is inside the Banach-Lie group of upper triangular operators and acts on the Grassmannian in a way that the flow that it generates gives the KdV equations, the hierarchy of KdV equations. What we get as consequence of this is the following. Yeah, perhaps I should go through this proposition first. So if you start with a Banach-Poisson-Lie group, so with the definition I gave before, if you look at this subbundle B of the cotangent bundle, is that B is invariant by left and right translation by element of the group. And if you take the space at the identity, this space is invariant by coadjoint action of B on its dual. And also, you have one cocycle on B with respect to the coadjoint representation. This is exactly what we had before. And so you can define the tangent the tangent Lie algebra by differentiating the Poisson tensor. And as I said before, if you ask that the Poisson tensor is with values in the tangent of the group, then you have also a Banach-Lie Poisson space. So I showed this before. So now we have the following thing. The restricted Grassmannian is an homogeneous space of the group of unitary operator on H with the condition that two blocks, the off blocks, are Hilbert-Schmidt. And there is this group U of H has a Banach-Poisson-Lie group structure. It acts on the restricted Grassmannian as in a Poisson fashion. And there is this dual Poisson-Lie group, which act also on the restricted Grassmannian by tracing transformation. And the symplectic leaves of this Grassmannian are exactly the orbits of this group of triangular matrices or triangular operators. And moreover, the commutative group that we had before acts in a Poisson fashion and generates the Cadivari hierarchy. So you have this setting when you have two Banach-Poisson-Lie group acting on, actually, have more precise here, they're both acting on the restricted Grassmannian, which is a homogeneous space of U of H. They don't act on each other, it doesn't make sense in this setting, but they act on the homogeneous space, which is the Grassmannian here. And one of these groups has a commutative subgroup which generate all the equation of the Cadivari hierarchy. Okay, so that's all from my side. Let me give you some such challenges in the infinite dimensional Poisson geometry. So nowadays we want to implement geometric integrators, meaning if you start with a PDE, for instance, the Cadivari equation or other systems, you want to be able to solve the equation numerically in a stable fashion. So this is a research on the Poisson integrator. So there is, for instance, the thesis of Coursera, and also other people working on this using algebroid and groupoid in the infinite dimensional setting. The thesis of Coursera is mainly in the finite dimension setting, but it's opening the research in this direction for PDEs. So that's one thing that we want to understand. How can we build Hamiltonian Poisson integrator for PDEs? And the main issue here is to have a long-term stability of. The second question is, what about one-channel splitting theorem? So, as I said, there are no Darboux coordinates in general, but can we have still a splitting theorem with some symplectic manifold and some Poisson manifold? That's one thing that we should work on. And also, there is a link between hyperbolic geometry, integral system, and Poisson geometry, which go with the work of Tenenblatt, Seppi, Takhtajan, Theo, and Wang. So this is also a very challenging perspective. I think I will stop here. I know I was a bit fast for some part of the talk, but please. Yeah, yeah. Yes, that's Frobenius in some very general setting. Just Frobenius, yes. Yes. Yes, indeed. I could also put Pelletier here. Yeah, indeed. Yeah. Yes. Pelletier is a French guy working on this infinite dimensional algebra at group weight, and yes. So all this, most of these people are coming from functional analysis and using Poisson things. Yeah. And other, it is expected not to work for Fréchet. It may work for Banach, but it's expected not to work for Fréchet. Yes.
When you say that there's no charts.
Yes. So what you could expect is that you have you still have a Darboux theorem, which gives it's constant, exactly, but that's good enough for the splitting theorem, I would say. Yes. But even this, the study of all equivalent classes of symplectic forms should be done. What are these? Even on a Hilbert space, we should study this. So this means took operators by bounded maps, group of transformations that acts on symplectic forms actually. So the space of orbits should be also investigated. Other questions? Yeah, please. Yeah, loop groups. Yes, indeed. So that's the work of Neb, I would say. Yeah. So here you have for locally convex Lie algebras, duals of locally convex Lie algebras. That's a more general setting.
Are only in the sense
Yes. Here's more. Other questions?
Thank you. So first of all, I did not wrote here. This is work in progress with Henrique Busching. And the idea is to kind of calculate the biggest coordinate chart for linearizing a standard Poisson structure in SU2. So here's some outline of the presentation. I will begin to talk about these Poisson Lie structures that Barbara already told a little bit about. So a Poisson Lie group is a Lie group together with a Poisson structure. And you ask a bivector, this finite dimension, and you ask the two multiplication map to be a Poisson map. And the product you consider the product of the Poisson structures. And this is equivalent to say that this Poisson structure is multiplicative, which means that it satisfies this equation. It's multiplicativity of the Poisson structure. And here's a simple calculation you can do directly from this equation. Is put G equals H equals the identity and the unit of the group. And then you get that this is a singular point, so a point where the Poisson bivector vanishes identity. Every time you have such type of points, you can consider the linearization of the Poisson structure at this point. And this is a Poisson linear structure on the tangent space of the identity then. And this is known to be dual to Lie algebra structures. And then this is what you get every time you have a Poisson Lie group. Then automatically you get a Lie algebra structure in the dual of the tangent space. But then again, this is a Lie group, so the tangent space is already a Lie algebra, so you have two Lie algebra structures, and this is a bialgebra. It's not the definition of bialgebra, but there's some compatibility conditions here, which is the Poisson bivector of one of these bialgebra, of one of these algebras, Lie algebras, is a cocycle for the other representation of the other. So this is actually a result from Greenfield. This is kind of a Lie correspondence. Every time you have a Poisson Lie group, a bialgebra. There are other ways to understand this with many triples, but this is kind of same of every time you have a Lie group, then you go to the tangent space, you get a Lie algebras, and vice versa. Of course, to go from bialgebras to Poisson Lie groups, have to consider simply connected Lie groups, things like that. But this is just the same type of correspondence, and this was what Alice was talking before. So what happens is this cocycle condition is symmetric, and then you can consider if this is a pair of Lie algebra, this is also a pair of Lie algebras, and they are both compatible in the same sense. And then every time you have a Lie bialgebra, then you can consider the simply connected Lie group, a Poisson Lie group that integrates it. And then you also get another group. It's also a Lie group, a Poisson Lie group structure, which is tangent to the bialgebra with the opposite directions, the opposite Lie algebras. So this is the general thing about Poisson Lie groups, and this nice category equivalence between Poisson Lie groups and bialgebras. I wrote here some examples. I'll pass this very fast, but basically, every time you have a bivector, you can consider left and right translations and take the difference. This is always a multiplicative bivector in the group, and there's this condition, which I don't want to talk too much about, but there's this condition to know when this is really a Poisson structure, when this satisfies Jacob equation. And if the group G is simply connected, then it's compacted, and every example appears. Every Poisson Lie group is like this one. It's that type of condition. But it's just a general introduction to Poisson Lie groups, very, very fast, very basic. What I want to talk about is a specific one, which is in SU2, or the standard Lie Poisson structure. And this is a general idea of how you get these canonical structures, the standard structure. You start with a real Lie group, K. You go to the tangent Lie algebra, small k. You complexify it, and then you consider it as a real Lie algebra. It's again the double of the dimension. And then as a Lie algebra, you can consider a simple connected Lie group that integrates it. So this is the complexification of a group, the idea of how to complexify a group. Of course, this is not the same group, this is twice the dimension of this one. And then every time you have, when the group G is compact, or semi-simple, this big group G, this complexification of K, has a natural decomposition as a product of three groups, one of them being K itself. This is called the Yarsal decomposition. And it basically gives, I should wrote here, but I forgot. But basically, you can decompose this Lie algebra of the complexified Lie group. Let me write like this. It can be written as K, direct sum of some other Lie algebra B, which is actually the sum of the tangent space of these two others Lie algebras. And I call it N. And if you consider this case, compact case, or semi-simple case, the Killing form, you can use the Killing form or the imaginary part of the Killing form to identify the second Lie algebra with K, the dual of K. The dualization is this pattern, the Lie bialgebra. And as a Lie bialgebra, it comes in this Poisson Lie group structure on G. Okay, in this case. So this is basically a general idea about a general way of saying. I'm trying to explain what's this canonical structure. If the Lie group is compact, every time you can do this little thing here with this decomposition to get a specific structure, Poisson Lie structure on G. Okay. And here are some, I call this section extreme examples, because they are extreme. When you have this standard structure, they are extreme in the sense of linearization. So here's a result by Ginsburg and Weinstein. If you consider K with this canonical structure pi here, and you consider then the dual Lie group, it's also a Poisson Lie group, it's actually globally linearizable. And which this means that you can find a Poisson isomorphism, the homomorphism between this Lie group and its tangent Lie algebra with its linearization at the density. So this is, in this sense, that I'm calling this an extreme example. So the dual, if every time you have this standard structure, the dual is always globally linearizable. So this is an interesting result by Ginsburg and Weinstein. We're going to talk about a little bit further about linearization, but let me first give you also this another extreme example. Suppose that K this is compact group with its canonical structure. If there's this result by Kain, Gutte, Hansley that says that if it's not SU2, or more generally, if it's not product of SU2s, when you decompose the group as product of groups, none of the factors are SU2, then it is not linearizable. And this means that it's not equivalent to the tangent space. Yes.
Poisson structure that you are calling standard.
Yes.
Is the one coming from this.
Yes. Exactly.
This one you call LW. Is all one.
Oh, sorry. It was supposed. I was supposed to change the notation.
I see.
Sorry, I'm sorry. But so LW means for Low-Einstein. But it's the standard structure. Yeah. The standard equals Yarsal. This is was defined by Lou and Weinstein. I didn't talk about this, but it was defined by Lou and Weinstein. So I was kind of Yash. Sorry?
You go back one slide.
Yes. So the more is every time you have a Poisson Lie group, you get a dual Poisson Lie group, and if you have and you also if the group is compact, you have a canonical Poisson Lie group structure. So you also have a canonical dual. This canonical dual is always globally linearizable. This is the result that by Ginsburg and Weinstein. Yeah.
So it has a chance of being diffeomorphic.
In particular, it's not compact. And also, it might be good to mention this is not this is a vector space, but it's not a Lie group the Lie group structure in this vector space is not the same here because this is a billion. Well, and so in this sense, this is the dual is always globally linearizable, while the structure itself is never linearizable. It's not linearizable. Yeah, this is always about. I'll give a definition of linearizable in a moment. But then the point here is that they have this hypothesis that K is not SU2. So this is where our interest comes from, because they say nothing about SU2 in the paper. So this is the question: what about S2? Is it linearizable? Is it not linearizable? If it's linearizable, how globally it is? So what's the maximal, some sense that you can find this linearization? And here comes this another thing that we want to talk about. That is this idea of how global it is that you can find the linearization of Poisson structure. But first, let's go a little bit. I try to make some slides here. Maybe I'll draw some pictures. This is me trying to tell you what's the linearization of a Poisson structure. So start with a Poisson structure in an n-fold M, and then you have choose a point P and a symplectic leaf L, and we also can choose here a tubular neighborhood embedding. So you have, imagine that you have the normal vector bundle, and you choose this psi. So this becomes a neighborhood. I'm assuming that the leaf is embedded. This assumption not always true. And then here in this, this is a vector bundle over L. You have this multiplication map that is just his scale. You take a vector and then you kind of multiply it by t. And if you think that t is a small value, t is near 0, then this is kind of, you take something that's big, you turn it small. Or if you consider the pullback of this map, by this map, for example, imagine I have a small neighborhood here in the tubular neighborhood, very small, and then you pull back it by t, so this is big. Right? As t goes to 0, I was calling this the zooming in isomorphisms. This is just to justify a little bit the notation. But this is the idea. The idea is that you have the Poisson structure defined around this leaf L, and you kind of want to consider germs of structures. So you can consider this tubular neighborhood to be very small. And thus, as these structures are getting small, the Poisson structure is becoming normal, some sense. So this is the definition. There are other definitions, but this is a kind of a quick definition. You have a Poisson structure on this normal vector bundle. You can define it by pull back in the Poisson structure to M. So imagine that you have psi here, and then here you have pi. Consider psi star of pi. This is defined globally because, but then I can pull back it here. K star of psi star of pi. So this is kind of, I'm zooming in the Poisson structure, the original one, but pull back. And I'm taking, as t goes to 0, this is going to get smaller, smaller, smaller. And I'm kind of open it and see what's happening. So this limit always exists, and also this Poisson structure always exists. Sorry. Yeah, this is just the pullback because if k is not 0, this is an isomorphism. So this kt is an isomorphism. You can always pull back any bivector, any vector actually. So what happens is this: this limit is always exists. This is something that you have to verify, and also it doesn't depend on the tubular neighborhood structure that you have. So this is a Poisson structure that you always get this in this linear model. Because there are other ways to explain. This is just a kind of fast way to say what's the linear model. But then these structures are such that if you consider at any point P, the original point P, if I have a transversal here, or a transversal here, this always this Poisson structure always induce a canonical one in every transversal. And this canonical one is called, I will be calling it pi linear, with small lin, L-I-N is above it. So just to explain this object, this is kind of a symplectic linear Poisson structure over a vector bundle. So what's this sentence means? This means that you have a Poisson structure in a vector bundle E, and the base is symplectic, and every fiber has a linear model. It's fixed. It's a vector space with a linear model, and locally the vector bundle is the product. The vector bundle with Poisson structure is locally the product of the symplectic Poisson structure, the basis, times this linear structure that you have. So this is the type of object here. You can kind of formalize what this means doing consider vector bundles over symplectic bases with a model, a fixed linear model, which is a Poisson linear structure on the fibers. It's the same, locally the same. You can trivialize all at the same time. So this object, this Poisson manifolds here, is what's the linear model for any Poisson structure. And this is the definition of what linearization means. So a Poisson manifold is linearizable in a point P if you can always find a neighborhood of the point P and this linear model. A Poisson isomorphism. Poisson is homomorphic to a neighborhood of P in the original structure. So this is basically here. Here you have a model here, and have the original Poisson structure. If you can neighborhoods, let's say this is the point P. Find a neighborhood here that can be turned via Poisson diffeomorphism to a neighborhood of P. Then you can say that's linearizable at P. So this is the definition. There are extreme cases when the leaf is a point. This is the usual case. If pi1 is just the point P. So this is actually a Poisson structure in TP of M. Poisson structure in TP of M. Okay, so basically I'm saying that if there's a local canonical linear model for any Poisson structure around any point, or around any leaf of the Poisson structure. Here are two points. So one for the double theorem, how you read the double theorem, or the double Weinstein theorem, and the other for how to read the cone linearization theorem. So first of all, let's consider this canonical linear structure on this, the fibers of the vector bundle, the normal vector bundle, or the transversal structure. Let's fix an isomorphism to a RK. So my RK, if I pass on linear structure pi 0. So this is going to be fixed from now on until we stop fixing it. So fix one of these. What you have here is that this linear model is the product of open neighborhood of R to L. Imagine that L is the dimension of fiber with the canonical symplectic structure plus K with this fixed structure that you chose in RK. So this is a way to read the double theorem. You can consider this Poisson, any symplectic, you call that L is symplectic manifold. Then you can transform, you can choose coordinates to turn it into an open set in R2K plus L, R2L, while this other part, the transversal part, you keep it because the bundle is linearizable. The bundle is already the product of something symplectic plus something that's Poisson linear. Then this is a way to read double theorem. That this local model is always actually a product of an open in the canonical symplectic manifold times RK with some fixed Poisson linear structure. And the way you read the cone linearization theorem is that if this Poisson linear structure, which is actually dual. Its dual is a Lie algebra. If this Lie algebra is semi-simple of compact type, then it's always possible to linearize. So this is the a way to say the Rabot theorem. The Rabot and Kohn theorem. Kohn theorem is the Kohn linearization theorem. So here is how we define the capacity, the Poisson capacity of manifold M pi at P. And you consider this fixed model and a point P, and you consider the supremum of R squared, where R squared is the radius of a ball that can be embedded in MM with this Poisson structure, taking 0 to P. And here, this embedding has to be a Poisson map with the structure induced from this product, that's this RK, this linear transversal structure that you chose, times the canonical one. So basically, what I'm saying is that you always have this model here, if you fix this linear Poisson structure, and the canonical one. You can always consider this as a model, and this capacity asks what's the biggest ball, what's the square of the radius of the biggest ball that you can embed in the original Poisson manifold. So here are some before the examples. You may consider that is so you always have to fix some pi 0 here in Poisson linear structure in RK, and if you want, morally you actually you are fixing, even here in the Rabot coordinates, you are fixing some simplex model here in R12. So it's not strange that you have to fix also a model in RK to be the linear part. But you can, in this case that we are going to consider, you can actually define something that doesn't depend on this choice of canonical structure. That is, you could consider between all these maximal radius for all linear Poisson structures transversal to the leaf that you can consider. You consider the sup between overall with model equal 1. Right? You normalize it. And if you normalize, this is also kind of calculate some kind of maximal radius that you can consider. So there's a definition that depends on the model that you choose. There is another definition that you can actually calculate the supreme overall of him, and it's not gonna depend on the linear structure that you chosen, the transversal linear structure that you chose in IK. So here are some examples. First of all, the symplectic. If I consider Poisson structure that comes from a symplectic manifold, pi omega, and then this definition is actually the same definition of the symplectic capacity. It doesn't depend on the point P, and it's exactly the same definition because the group of symplectic morphism acts transitively on the manifold. Another example is when you prove that something is not linearizable, like the other result by Kahn and others. You're actually proving that this capacity is 0. You cannot trivialize, so it's if you cannot find a neighborhood here that trivializes, then the maximal radius is going to be 0. And also, in this case, it doesn't depend on the linear model that you chose. Right? If you all linear model needs to be isomorphic to just make sense. And finally, in general, if you are in this hypothesis of Kohn, that's this linear algebra, this transversal linear algebra is semi-simple of compact type, then it is linearizable by this result of Kohn. Or in general, when it's linearizable, not only in this case, this symplectic capacity is positive. It's bound over by the usual symplectic capacity of the leaf. Because if you can embed a ball here, then you can also embed a ball in the leaf, right? So it's not really limited by the symplectic capacity of the leaf. But in general, this leaf can be this capacity of the leaf can be infinity, or the maximal ball can also be infinity. So these are the definition of capacity that you consider, and what I want to talk about is this result. In the case that you consider SU2, not only with the canonical Poisson, the standard Poisson Lie group structure, not only it's negligible, but you can calculate. You can actually calculate this explicit this capacity. This capacity is gonna be this one that doesn't depend on the model that I defined second here. This one is actually pi square over square root of 2. You can calculate exactly. And for now on, this is the goal of the rest of the talk. So the SU2 case. So how do you linearize it and how you find this maximal linearization? First of all, let me talk about, I was too vague when I was studying this structure. So here's an explicit way to, explicit formula for this Poisson, the standard Poisson structure. I still call it sometimes Lou-Einstein. I was calling Lou-Einstein. So I will use these names interchangeably. Lou-Einstein or standard. So in A4 you consider this kind of Poisson bivector. This is a Poisson bivector, and it's kind of quadratic here, and it's restrictable to S3. When we identify SU2 with S3, this bivector restricts to the standard one. So this is the formula, and from now on, kind of, I'm not gonna make any calculation, but I just tell you the nature of the calculations at least. So first of all, let's understand a little bit about this. Have this canonical simplex structure. Let's understand the lifts of it. And there's two kinds of lifts. The lifts are simplex manifold, so just dimension 0 and dimension 2. That's S3, and in dimension 0, this is the Vanish setting. The setting the Poisson structure vanishes, and this is just the circle. So you have S3. Let's imagine here like a S2 circle, but then this is I have here A2. I want to think this H has complex map. Okay, so of S3 with this H2 circle. So this is the Vanish setting. So every point in the set is a leaf. The other leaves are the other simplex leaves are some type of spherical caps. And this is let me just draw this picture. So you have R2, and here you have the complex plane, but you can always choose some real direction, which is the direction of the angle theta. And this becomes some, I call it R3 sub theta. And here you can consider spherical caps, or positive spherical caps, which are just the vectors in this R3 space here. This everything is R3, which have norm equals 1. Every one of these vectors can be parameterized by the circle. And here's how you consider. These are the leaves, the two-dimensional leaves in S3. You can kind of imagine here in this, if you can consider this image like this, and have complex, and every time you fix some direction here in this complex plane, you kind of have a spherical cap with the same boundary. The boundary is the intersection of H2 with the circle. And then if you choose a different direction, you can kind of find another spherical cap. So I have this picture that you can. The intersect is only on the boundary here. They all have the same boundary. That's the Vanish set of the Poisson structure. So this is the kind of, if you have a Poisson structure, you say which are the leaves, the simplex leaves, you kind of understand it better. Practically, this kind of thing should be the picture that you have. So for the linear part of this, for the fixed, the linearization, book structure here, which is given by. Let me just draw another picture. The idea basically is the following. So these spherical caps here. They are positive spherical caps. They're circles. They are geometric circles. So you can fix a point here in the boundary. Here you have the unit. I'll fix this point x0, which is minus the unit, and then you can apply inversion or a projection, spherical projection, to the tangent space here at the unit. And this projection they take circle passing through x0 and turn into lines, and they take spheres, two-dimensional spheres. They take two planes, two-dimensional planes, and then basically you can kind of invert it, and basically let me. Okay, so you can define this map here from S3 to R3 minus this point x minus the identity, the unit. We'll kind of consider the spherical projection. I will draw a two-dimensional thing here. So x0. Then you project everything here. And if you have a circle here, a geometric circle, it becomes a geometric line. If you have a spherical cap, it becomes a semi-plane. If you have a sphere passing through x0 here, it becomes a plane. But if you have a semi-sphere, it becomes a half plane. So what happens here is that when you apply this map, this singular set here, of course with exception of x0, but the rest of the singular set becomes a line. And this line is this thing that I'm calling coordinate t. And the other spherical caps here, as you vary theta, they are going to become half planes. So this is an example of a half plane. Everything here, everything for with boundary, the singular set. And then if you vary the angle theta, you're going to have another one. And this variation here. So what we'll get here is an open book decomposition of F3, which is, these are the leaves. So basically this is kind of easy to understand. We have F3. Let's think coordinates TUV. And then just this axis here is the singularities, and these things here are the leaves. These half planes with boundary, these half planes as leaves. And this angle theta here is also the same angle theta here given by this R3 space. So, so you consider this map that turns this sphere, you invert it, or you with the spherical projection to R3, and then it becomes the Poisson structure becomes another thing, but its leaves becomes the open book decomposition of R3. And with the open book decomposition, we have this Poisson linear structure here. And this is what I'm calling pi book, which is this Poisson linear structure whose leaves are going to also be exactly like the same one that are. So when you calculate this push forward, you take the standard Poisson structure in S3 and you push forward. It's not going to be exactly pi book, but it's going to be pi book times some function that doesn't vanish at any point, which is this quadratic function here, plus 1. So this formula also proves that the linearization of pi standard is actually pi book. So this is a model, and this is the model that we are gonna fix to calculate this capacity, Poisson capacity. Then we're gonna normalize everything. This is the idea. So you see, I told you that this is gonna be linearizable. This Poisson structure is not linearizable, but via this map F, this is not linear. It would be linear if it was pi book. It's not pi book. It's a function times pi book. So this is not linear. These functions here should be constant to be linear. So you still have to linearize, and there is an interesting way to linearize this, which is should be a proposition, but I'll just draw a picture, another picture. So you can write this pi book structure by some function f. And the idea is basically you have this pi book. There's this part here, that's the t, that's linear. It's actually the Euler vector field. And if you of course you just take this part here and turn it into the t tilde. So then it's gonna be a pi book again. So what we do is consider this plane R2 times 0, and here you have R2, this strange structure, let's say here, and the problem was that you want this turn this into dt. So what we do is you go through the flow of this vector field here, starting with this subspace here, R2 times 0. I think this is what I wrote, probably, yes. So basically you use this as parameter. So you have a point uv, and then you consider height t, and then you throw it here via the flow. You still put uv here, but then up here you consider the flow f dt at uv. So this is the map. You can define a explicit map here, and depending on the size of the flow of this map of ft, you can at uv it will be defined more or less depending on uv. This is the interval, the maximal interval of definition of this flow ft. So you can kind of turn it into, this is the map, right? I wrote here. So if you push forward this structure, it will become f times pi book, but then the domain of phi is going to be limited. It's not going to be everything anymore. But it's not a much serious problem, and then I can write here a corollary, that is this is the linearization. So if you consider the canonical structure of FSS2, it's take out a point. So this is globally, is equivalent to pi book but defining this open set here. And then I can write a picture of this open set, because it's symmetrically, rotationally symmetrically. So it's kind of the graph of this function here, if you consider u in v fixed. So it's like, let's consider like something like R, and then it starts at pi, goes here, goes to 0, infinity, minus pi, goes to infinity. So these things between these two here, so this is the leaf, right? The semi. Before it was a semi-plane, now it's just some graph, something between this graph. But then you consider this rotation here, the semi-angle theta, and these are the new leaves, and this part here is still the singular set. So it's this strange open set here, that is the open set that you can linearize. So no, so then you can say now, so you can consider the maximal ball here that you can put inside this thing, and this is a inferior boundary for this capacity. But we want to calculate the exact value, so it is not going to be the exact value. So, but this is the stat. At least this proves that it's positive, and it kind of gives an estimate. If you can calculate this exactly, but I did not. You can, because it's not going to be the capacity. So to find upper bound to this ball, you can consider the following modular vector fields. This is what I like to call volume tricks. So what happens is there's every Poisson structure comes with a natural invariant, which is this called modular vector field. I'm calling it x1 pi, and it's kind of defined using Hamiltonian vector fields for every function. You fix a volume form, omega or vol, And you calculate the divergence with respect to this thing, the Hamiltonian vector field. And this also defines a unique vector field here. But it's not unique because it's defined modulo Hamiltonian vector fields, but then the class here is going to be uniquely defined. So I always have this class. It's Poisson class. Every Poisson, it's a Poisson invariant, and it doesn't depend on the volume. And every time you have this some Poisson class here, you can consider the set of vanishing, the vanishing set of the Poisson structure, and if this is a smooth manifold, it's always in the case that's linearizable, then you can kind of restrict this to the vanishing set. And this is a vector field defined on the vanishing set, and it doesn't depend on the class also, because every Hamiltonian vector field vanishes at the vanishing set. So this is actually this vector field here defined only on the set of where the Poisson structure vanishes is a Poisson invariant. And then what happens is that what's also invariant is the maximum interval where this thing is defined. So you have this, you can state this reality here, that every time you have two open sets which are Poisson isomorphic, the R3 is Poisson isomorphic with respect to the open book linear map, their vanishing x needs to be the same, or the same length. It's basically because why, right? Why? Because you can compute this vector field, modular vector field here, and like 2 times this velocity. It should be like linear. You can calculate the maximum interval that it's defined. And here we have for this structure, it's actually the SU2 minus this point x0. So the maximal ball that you can put here, any other ball that you can put centered at 0, will intersect this singular set. I think that has maximal size 2 pi. So the maximal radius is a superior bundle for the radius. So the maximal radius is pi, and then you get this. So this capacity with respect to this specific book here, it's maximum pi. So the claim now is that is actually equal pi, and you have a superior code here. You want to prove equality, you just need to find an element here. So it's possible to embed a ball of radius pi here inside this open set. So, but it's not this one that you wrote here. You have to somehow modify it to get this ball of radius r. But here it's not hard to understand a little bit about this. If subgroup, we have R3. Take off this singular set. There is a canonical, this is isomorphic to S1 times R2. And this pi book is chosen exactly in a way that if you consider this trivial isomorphism between these two here, the pi book becomes 0 in S1 times a canonical form R2. So this becomes the symplectic part here. But you have to take off the singular set. But every time you have a Poisson automorphism, or you take a Poisson map between two open sets of R3, rotationally symmetric. So they will induce a map from S1 to the symplectic homomorphism between these sets that are turned around. So basically, what happens is this: you have this thing here, and then you can kind of this is logarithmic scaling. You can consider. Then now you forget about this part. then become something in R3, R2, but now going to infinity. This goes forever. And here's our open set. That's U0 that you rotate here and then get what U is going to be isomorphic when it comes from that to R2. And if you want to turn this in some other open sets, you just need to apply some map that preserves area here. I don't know. Let's write something like that. And then you turn this into some V0 and consider, and then you go back via this from R2 to R3 minus 0. And then you consider the rotation of it. This is kind of a representation of the Poisson pseudo-group of automorphisms for PyBook. And so basically you have this set U0 that corresponds to this symmetrically, the standard structure and the symmetric open set. And then you can turn it to normal symplectic morphisms via area preserving morphism to another symmetric. So this is kind of the general idea. And then in our case, U0 is this set here, this pairs of R2, which is T is bounded by this thing, this kind of this U0 here. It goes to infinity there, but the height is bounded by pi. And then you kind of, there are ways to find symplectic morphism maps transforming areas. In this case, you use the fact that this area here, and you go to infinity, this is finite. And you can make things explicit. Consider this specific function f here, log r minus some integral. I'm not gonna go further. And then you consider this type of map here, Ts, T over f prime of s, fs. This is a symplectic morphism map that preserves area. And then the image choosing this function f here is this here. Yeah, this V0. And this V0 is nothing but, so let me update here. And you have here height pi, height minus pi. And this is just this infinity. And then you go back to r minus 0 with the isomorphism. This becomes now it's in R3, something like that. And then you can kind of rotate around the Tx. So if you use r equals pi, then you can embed about in here. And this is kind of the consequence. Here I wrote for every positive r, this thing here is actually some of should the product minus pi times the disk of radius r, which is this disk here. And then as a corollary, the Poisson capacity of S2 with respect to this choice of linearization, a linear model in R3 is exactly pi. So this is how it is. And here's just a final word about what about the case that you don't want to choose the model, take any other model. This specific case, if you have anything that's isomorphic, linear Poisson structure in R3 that's isomorphic to PyBook, then there is it's just a linear algebra thing. It's actually going to be lambda, some positive number lambda, times the push forward of by isometry in SO3 of PyBook. So if you apply isometry, it doesn't change the radius of the ball, so it's not a problem. But this constant lambda will change the norm of the vector. In fact, it is actually the norm of pi0 over square root of 2. And then you can rescale everything, and that's why you have to divide by square root of 2. So that's all. Thank you.
SU2 times SU2 times SU2. There it would just be the thing. Or can you use it to compute it there?
Yeah, let me think for a second. Okay, this gives a lower bound for the capacity, but I'm not sure. S2 times SU2, you can find the same pi square as lower bound, but it's not totally clear. I think it will be also, you can also, but you have to go through some, you kind of calculate the modular vector field for the product, and to prove that's an upper bound, you have to calculate the period of the modular vector field. But then I think it will work exactly the same. Now thinking about calculate the even if there are lots of factors, I'm not sure what will be the modular vector field, but there are some things that we didn't talk about today, but you don't actually need the modular vector field to find these upper bounds. You can take other types of vector fields, but okay, you can take different classes in the SU case to conclude the same thing, to find this kind of upper bound. But so if you take product of SU2, I believe the capacity is going to be also pi square over square root of 2. Começar a fazer barulho, eu pensei que tava tendo uma infiltração assim.
que así está bien. Bien, no tapar la luz. No tapar la luz.
Okay, so we're going to start with the last talk today. So our next speaker is Nicolás Martinez Alba from Universidad Nacional de Colombia. He's going to speak about Poisson and Riemann compatibilities and equilibrium.
Okay, thanks, Christian. Thanks, organizer, for this opportunity about this project. It's a joint work with Andrés Vargas. We will share with you. I will share with you of the results that we are getting about Poisson and Riemann compatibilities. Well, what's the idea when we have two structures in the same space? We want to take them and find some relation that put them together. And after that, which is its consequence. Today I will talk about the Poisson and the Riemann and look for a suitable condition that relate both. Before that, we begin with the usual, that is the symplectic case, where we have symplectic form and a metric, which is the condition that relate both. The usual is the Kähler structure, that is the metric, the symplectic, and an almost complex structure. We have compatibilities. One is the linear one, that take the transform two of them in the third one, and the other is the geometric. And the geometric is this one. We take the Levi-Civita connections and put that the two form is parallel. Well, but this condition we can also define without the almost complex structure. So we just need a connection that is torsion-free and is metric. This is called a symplectic connection, and it was studied by Cahen and Good. So the question now is, well, what about the Poisson? Can we consider the same compatibility? Of course, the same is changing what we need. The metric goes to the Levi-Civita connection, and the two forms will be the bivector. So when we want to do that, we just consider two things that changes when we use bivector instead of the two form. The first one is that the two form, the two form takes tangent to cotangent, but the bivector changes the direction of the arrow. The other condition is deflation, because deflation gives you two directions, one on the leaves and one transverse. So now, two other things to talk about. So interesting facts before we go into the compatibility. As I said, this is a natural way to extend the compatibility. Take the Levi-Civita and put the bivector by Lignerowitz. But Weismann in Poisson structures show that we consider this condition, foliation is regular, must be regular. So we have a lot of examples that we can work with. Examples, this type of examples we can work with. Another consideration was by Fernandez, who works with bundles, principal bundles with base Poisson manifolds. In this case, that always you can construct a contravariant connection where the Poisson is always parallel. Parallel in this sense. So the question now is, we have here two problems, or two issues. One is regular foliation, and the other is if you switch to a contravariant connections, you always have a parallelism like you want. These two issues can show covariant data, that is this Levi-Civita connection is covariant for a contravariant, that is the thing that work, and we must consider the foliation and the metric at the same time. So we can deal with both situations if we define these new connections. So first, this is contravariant because we are defining on one forms, and it is metric, the metric part, so we need a connection, contravariant, metric, free. The node connection is Levi-Civita, but it's covariant. So mimic the definition or the property of the Levi-Civita, but in the contravariant way. How to do that? You a pairing. A way to derive the pairing, well, we use the bivector to consider the vector field, and we need a bracket. In the case of vector fields, it's the Lie bracket. Well, now in one forms, we have the bracket by vector. So this is the usual Kosul formula. It was used by Buscetta and worked with the same idea of parallelism, but with this connection. But what? Thanks, Enrique. This pairing is a cometric. The quota. We should consider one is the way that it's universal, but so we need to consider both with the cometric, as I said. And we begin with our first definition. That is, how can we consider the compatibilities? We have four of these. The Casimir invariant. What is Casimir invariant? Well, a nice computation is that we have a function. We always define a vector field that is the Hamiltonian. This is Poisson data, but we also have a metric data. That is the gradient. How is defined the gradient? Just put the metric, and this is equal to the differential. So when you input a vector field, input it here, and is computed by the metric. So take the input, but of this form. So here we have this one. This part, this generates the tangent of the leaves. And part is just the computation of the bivector. Put a Casimir function, this vanish, and this will be tangent, orthogonal to the leaf. So that's the idea. The first definition is taking a Casimir function and derive the bivector on the direction of the metric, that is the gradient. A parallelism, but just on the direction of, look, this is perpendicular to the kernel. And a transversal parallel is to take this vanishing only in the direction of the kernel. Together, like we are. considering the two issues before, this one, metric and torsion free, but contravariant. Okay. Some examples. These are like toy examples. First one is take the Euclidean metric here. This is the Euclidean metric, and put a conformal function here, a conformal version of the Euclidean metric, and also the same conformal, but for the usual Poisson, but in R3. Looking that we are not considering the we get wise, leaf-wise, vanishes on the leaves, but it's not completely parallel. But if we change a little bit this conformal metric, look, this is O-metric. Take this one is like planes, only consider the Poisson on the X, the Y directions. So here is totally. Sorry, I forgot to say that completely parallel in the literature is also known as Riemann-Poisson structures, like Bouchetta introduced it. And is Riemann-Poisson or parallel in all directions. Another example is SO3. SO3 only vanishes the bivector when take the directions on the a difference to these planes. It's a just exercise here that if we want to move a little bit this bivector, I move by a function on the radius in order to obtain this vanishing. We have that this conformal part is linear. So, by this reason, we consider this movement on the Poisson structure. These are then is completely usual, that is neither Casimir, neither this condition, but moving a little, it becomes completely parallel. Okay, some simple example. So, I move to a comment that a result by Fernandez. Fernandez defined a contravariant connections. Again, principal bundles. I just want to put here some results he did. One is called an F connection that works in this way. This D is the connection, contravariant connection. I derive on the direction of one form, and this will vanish only on the direction of the kernel of the bivector. This is called F connection. When he get the connection, he also want to define the parallelism. And again, this is called Poisson connection. And if he put these two conditions and torsion free and if D is torsion free, this three condition implies that the connection to the leaves. What it means that on the leaves, it look like a connection, but only on the leaf. It's not the exact formula, but it's the idea. The idea is that he can derive only on the leaves, on the symplectic leaves. So the question now is, this is another connection. This comes from a principal bundle. We are defining a connection like a causal formula, metric. So the question is, this condition also holds? Again, we can restrict. And the answer is, okay. If you put alpha and beta in the perpendicular distribution and put gamma in the other way, it's blue? Okay. This work? Not for the moment. But we consider the result for the moment in the regular part. Then the causal formula that I suppose concite in this case one. The 6-term formula, 5 vanish, and only we get here and get this result. The connections only lives in the part of the perpendicular. Is the same as this distribution is involutive under the bracket on one forms. And the nice thing is that this condition is equivalent to have this Casimir invariance. So we are obtaining a similar result as Fernandez did. And the other part, Enrique's question, what about the foliation? What about the regular? These results are in the regular part and says, when you have the transversely parallel, you get a bundle-like metric. And when you have the leaf-wise is in the leaf, you have a colored structure. It's very nice. So I go, well, and if you have both, okay, you have both. Bundle-like and color. But I want to stop a little bit in the second. The second says, you have symplectic leaves. You have the compatibility. So what happened in the leaf? The leaf becomes a color manifold, but with other metric. You have the symplectic form in the leaf, and you take the restriction of the metric to the leaf. You take a scale and a rotation. In that case, they become a color. Not with the same metric, with other metric. And the first one, what is the first one? The first one is bundle-like. The interpretation of bundle-like is very nice. The definition is not so beauty, but the interpretation is very nice. The definition of bundle-like is that you have an element tangent to the leaf, and you have two vectors, and these are sections, two sections of the perpendicular. So you take the derivative on the perpendicular directions, and the derivative is 0. This is the definition of bounded lake. What is the interpretation? Interpretation is that when you take the perpendicular directions, the perpendicular directions jumps from one leaf to another. So says that you jump from leaf to leaf in a constant way, is that you are further away constantly. So the distance are constant. The complex on the leaves? Well, do you remember the construction of color structures in a symplectic case? You have a metric, you have a symplectic, and you have a rotation that to take the linear compatibility between both, you must consider a linear transformation that is the square root of some matrix, same way. And the nice thing is, like the variation is smooth, and these changes of the complex structure, so like a spoiler is, if you put together, you glue the complex, also obtain the Riemann and the Poisson. Some examples. Oh, the color is not the best, but can you the graphics? This is the open book that Hudson says. These are the pages here. These are cylinders. Sorry by the color. It's not very good for the presentation. And these are planes. So, what can I say? Here, if we, in the one, the first is R3 with the Euclidean metric. And we'll put this Poisson structure. Okay, we have planes. My symplectic lifts are on the y and directions, and fx is a Casimir, so it only defines the position of the leaf. And okay, so look to other leaf. So the question here is that they are colored and they are bundle-like. Bundle-like is also called Riemann foliation. When this function is constant. So, well, that's natural, no? Because you are jumping from one leaf to other by a constant term. And if you want to take the color, well, it's constant again. So you have just a constant change of the symplectic form. Again, in the F is, and the cylinder, let me see what I say about this one. Okay, this is for the planes. For the open book, we consider this metric in cylindrical coordinates. Look, it's the co-metric. And I take the Poisson. Hudson wrote the Poisson in the coordinates. I write it in the cylindrical coordinates. And look, again, I put this one depending on theta. That is Casimir for this Poisson. And what we get is that the foliation is a Riemann foliation when there is no changing. that says that the move leaf to leaf, depending on the angle, is constant. And same way in the cylinder. You change from one to other just by jumping constantly. That's the interpretation result. So I focus again in the color situation when it's a leafwise parallel, in particular when it's Riemann-Poisson directions. The color structure compatible with the symplectic structure, but maybe the metric must change, must rotate. And a brief recall again is the color situation is the symplectic that transforms the tangent to the cotangent. The metric, again, tangent to cotangent. Linear compatibility is the almost complex that take tangent to tangent, and the diagram commutes. This is the usual one. The J is almost complex. It means we have relations, and I said in the first slide, the geometric compatibility can be written as omega is parallel with respect to the Levi-Civita. So the question, how it changed? Remember, one of our change was the contravariant situation. So I must the arrows in the other way. If we change the arrows, I have acometric. Sorry. Put the same arrow. Sorry. The Poisson and another J. I put like a small hat here, small t here, and take this again. This diagram commutes. Is this one? Is equivalent to this one. Is equivalent because the omega is parallel and the J is also parallel with the same Levi-Civita connection. And here we have to add an extra condition because the metric is an isomorphism. So if we take the pi with kernel, and this is isomorphism, the kernel must be the same. In fact, J must have kernel. This diagram says that in particular, if we want to extend the almost complex situation, I must have that the bivector has the same kernel as this bundle map. That's the reason that we have a G squared plus identity and changed by G to the third plus J. This is linear, so they have a kernel lambda equals 0 as an eigenvalue, because we need to consider the kernel. And the other, the integrability will become that this J is parallel with the contravariant connection. And our theory is that when you consider now the three structures, the cometric, the bivector, and this co-complex, we call it co-complex because contravariant, is called color Poisson when it's parallel, and the color Poisson produce again color foliation. But in this case, the metric is the same. In the previous case, in the Riemann-Poisson, just take the metric and take a rotation. Now, the metric that makes the color structure on the leaf is the here a small summary of some examples. It's very nice. Here we have R3 without the origin, and take the SO3 structure. And as I said in previous example, if you consider this alone and G the Euclidean, we have problem with Casimir. But if you correct by a radius term on both radius in the bivector and R square in the metric, this is compatibility. And also, when I said that it's compatible with a almost complex structure, is that the spheres are complex. When I go maybe any constant, but in order to take a color, the constant must be 1. Is the most rigid situation. And these are ones. This is the cylinder. Again, the cylinder, but look that we are changing the co-metric. Here we are taking control on the radius coordinate, and here we're taking control on the angle coordinate. And this is the open book situation, and these are the conditions that we have all the compatibility. These are just differential equations, all the possibles. But we only talk about the regular part, as Enrique's questions. So, what about the singular part? Because here in the we can consider an f that vanish on x equal to 0. For example, vanish on all the points as Hudson says, the singular points are all the points on the x. Each point is singular. And in the cylinder, all the points on the x is singular. And are they color? How consider the foliation? Foliation from one cylinder to other is the jump. Is this jump? I erase this jump. Constant jump, constant distance between leaves. Just the distance is the radius. Here the distance is the angle, and here the distance is the x. What about the singular? So we must go to the definition of what is Riemannian singular, which is singular Riemannian foliation. And the definition is the following. So take a point, a singular point. Singular point. Take a curve that passes through that point in time 0. If you take a geodesic at this point, the geodesic that is perpendicular to the leaf, then that geodesic must be perpendicular to all the leaves. So when you take the geodesic and all these tangents must be tangent to all leaves. That the geodesics is true. That's the definition of singular foliation. Can you see the red arrow? A little bit. These are from singular points. Look, these black arrows are tangent to the geodesics through the leaves, through the regular leaves. Look, this says that this black arrow from this cylinder, they cross one perpendicular. Also these are crossing the planes perpendicular. Here is not so easy to see, but recall that the geodesics in these directions are the circles. So yes, there are passing tangent to the planes. But the singular, if you take a point here that is singular, you take a geodesic that cross all the points but no the planes. Or from a point, they cross all the planes but diagonal. Also here, first this one. Also this diagonal, this dot arrow is going down, so they are cross all the cylinders but down, so it's not perpendicular. Also, you can take a point and, well, there is a red arrow. I draw a red arrow for in the axis. I can see it here. And this is the worst scenario, because you take a point and you have two options, or point up, point down, but leaves in the axis, or point in any other direction. But any other direction always belongs to a leaf. They don't cross it perpendicular.
Example, the singular set, the first one, is
Each point of the planes x equals 0 is a point. No, each one is dimension 0. Each point is a leaf. Each. So this is an very bad. So let's see a little bit this Poisson structure and consider consider the Euclidean. When we have the Euclidean metric, note, in the singular Riemannian foliation, we are taking geodesics. If I talk about geodesics, I must consider the covariant connection. Okay? So now I want to use the covariant on tangents. And take R3 on points of the axis with this bivector and with the metric, the Euclidean one. To compute, because the Euclidean, the coefficients of the Euclidean are constants. So derive the bivector by the Levi-Civita is just derive the x and the y. So we get dx y minus d theta. It's not punished, okay? But when I compute the derivative along these directions, computed again on dx, this one, the So we have this one. But we can consider this particular one form, that is dx plus this, and take the dual. The dual by the metric. Dual by the Euclidean metric is this. And I will, I'm talking about geodesic. So maybe it's better to put here in order to get that this direction is tangent to a geodesic. This is just this constant and compute So this is one example of the previous situation, that is singular foliation. You know, in one of these examples, we get this, then it is not zero. Our claim was, okay, so the condition that we must look for is exactly, is exactly that this derivative must be zero. So this is strange. This doesn't appear in the in this talk. But why this appear? This condition appear? Because the following is that. Sorry, I forget something here. Okay, this is one. Because I have this. There is a problem here. Okay. Because we have this one. We can pass through from this, that is was the computed there from a geodesic, the covariant derivation about geodesics. I can pass through a contravariant. And look this form. This form is the derivation of the tensor on this same direction. Must vanish. And this relation is also known in the covariant sense. In the covariant, there is an identity that is the derivation in the x direction of the almost complex on the x direction. Look the relation. This is covariant, this is contravariant. Equals 0. This is known as nearly Kähler structure. It's also known, it's also worked. So this motivates us to consider this situation. It's also known, but we change it to the covariant, contravariant case. But what's the problem? The problem is that we are deriving on singular points. So we have problems to take the derivative. In order to get singular foliation, we should consider this situation. Derive along the direction of the kernel of this covariant, because we are dealing with geodesics. So I have here the translation of the one form to vector via the metric, but taking the n derivatives, not one, not the first one, but the first, the second, the third one, all the derivatives, because I need to control all in all directions. Oh, sorry, all derivatives, but only on the alpha directions. But I must put the condition that the geometric structures, I mean, the cometric and the Poisson structure must be analytical. Putting these things together, we get that the foliation is singular Riemannian. Yes, I'm asking this condition for the pi. But for example, if I take that the nabla pi is symmetric, we get it, this condition. It's not so hard to ask that condition, because we have examples where this is skew symmetric. So this vanishing is automatically. So this condition is not so hard. And also we have, if structures Poisson are analytical. So we have some examples to do that. And this is how we can deal with the singular part that answered why these are not singular, but which are the condition to understand the singular part. And that's it. This alpha sharp is the metric. Is the metric. Is because you have the G is an isomorphism between the tangent and the cotangent. So if I take alpha here, this is your alpha sharp. And that's the derivation on this direction. We get singular Riemannian. All of these examples have improving that here we have some direction alpha that does not vanish in this derivation. That's the condition we should ask, but not just the first derivation, but all the derivations. To put all together in the analytical setting to take the limit to the singular point. This is very, very strange, because we are considered this the symplectic foliation. The symplectic have, for example, in the cylinder, we have each point is symplectic, is singular, each point. And we have the foliation, cylinders, point, 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 point. But if you look that foliation as a Riemannian geometer, you don't see the points. You see all the line. And if you see all the line, it becomes singular foliation. Why? If you the lines, the perpendicular to the line always hit transversal the cylinder. That's the difference between the singular Riemannian as Riemannian geometer to the singular symplectic as postulator. That's why this condition is too hard for the moment.